Hello everyone, welcome to this video. Today we are going to continue studying switch capacitor converters. Here is the outline of this presentation. We are going to see first an introduction and then we will deal with two issues in switch capacitor converters. The first one is how to implement a soft start, and the second one is how to implement switch capacitor converters with the capability of bidirectional operation. And along the video we will see several simulations to illustrate these aspects. This is the fourth video in this series. Before this video we have seen the videos number 17, 18 and 19 related to switch capacitor converters. So please, to have more information, take a look at these videos. We are going to continue using the inverter SCC as an example. However, the ideas that we are going to see can be easily extended to other topologies of switch capacitor converters. Remembering the operation of the inverter SCC, we have in total 4 switches. We have this switch here on the top and this other on the bottom that are controlled or driven by the signal phi1, and the other two are driven by the signal phi2. So as we can see here, during a given interval we are activating the two switches that are connected to phi1, then we have a dead time, and then we are turning on the switches that are connected to phi2, then we have another dead time, and then we continue like this in the operation. So we are going to generate here at the output a negative voltage with respect to the input. We have analyzed these converters in previous videos using this configuration here, the unidirectional configuration implemented with MOSFETs, 2 MOSFETs and 2 diodes. And then we obtain this characteristic: the output voltage versus the output current is going to behave like this straight line here, which is given by this expression. We have seen this before, so I am not going to enter into more detail. The equivalent circuit, the average circuit of this converter is given by this drawing here, and then we can obtain the output voltage like this, and also the efficiency of our converter, which is given by this expression, which at the end is the ratio between the output voltage and the input voltage. Now we are going to deal with a real aspect of the implementation of a switch capacitor converter, which is the startup process. Imagine that we have this switch here to connect our converter. We are already injecting the signals for driving the switches. So when we close this switch here, then at the beginning what is going to happen is that this capacitor here has 0 voltage, is totally discharged. So when we close switch M1, we are going to have a current circulating like this, which is only limited by the series resistance of the switch, the series resistance of the capacitor, the series resistance of the diode, and even the series resistance of the battery itself. So this series resistance is very small, as we know, so the current is going to be very big. If this current is high enough, then this switch M1 can fail, or even the diode can fail, so we need to limit this current during the starting up of the circuit. Similarly happens when we close switch M2. When we close switch M2, capacitor C is going to be charged up to the input voltage, and then we close switch M2 and we have a current circulating this way, which again is limited only by the series resistance of the circuit, because this capacitor, the output capacitor CO, is also discharged, totally discharged. so we are going to have a very big current circulating through it and through the rest of the elements. So these situations can put at risk the integrity of our switches. Once the converter is operating in a steady state, capacitor C and capacitor CO, they are going to have a DC voltage, so the difference in voltages are not going to be so high and the currents are going to be much more limited. Let's illustrate this with a simulation. Here we have our converter that we have seen before in previous videos. We have the input voltage 12 volts, we have the two switches, the two diodes, and then we are using these sources to control the switches as we have seen in previous videos. So let's see what happens when we perform a transient simulation from the beginning. So we are going to analyze the current that are circulating through the circuit. Let's run the simulation. First we can see the output voltage to see if everything is okay. So we see now that the output voltage is reaching the expected value, which is around minus 10.3 volts at the output, because as we know we have some voltage drop in the diode, so the output voltage is a little bit lower than the input voltage in absolute value. Okay, but now we are interested in the current, so let's take a look in another pane. Let's take a look at the currents that are circulating through transistor M1 and also through transistor M2. So we can see here at the beginning how we have very huge peaks with a very high amplitude of the current. If we make a zoom here in this part, we can see that the currents that are circulating are beyond 300 ampere. So this is a very large current for the transistors and they could fail during the startup process. If we take a look at the steady state, then we can see that in this part here, the value of the current is much lower. For example, let's take this one here, we can see that the value is around 24 amperes. This is because the difference between the three voltages, the input voltage, the voltage across capacitor C1, and the output voltage, the voltage across capacitor C2, are not so big now, so the current is much more limited. A very simple circuit to implement a soft start for switch capacitor converters is to use an RC network at the input, as we see here with this series resistance and this parallel capacitor here at the input. We can get an input voltage that is going to increase slowly in time, following like this an exponential evolution in time until the final value. So in this way we are not applying the full input voltage across the switch capacitor, so the currents are going to be much lower. Let's investigate this a little bit further. We can analyze the behavior of the switch capacitor converter at the input by using this equivalent average circuit here, in which we are assuming that because of the frequency of this input current is very high compared with the cutoff frequency of the RC circuit, we can assume that we have here the average value of the input current. So we can analyze this simple circuit to calculate how it is going to evolve in time the input voltage and also the input current. This circuit is very easy to analyze. We can obtain these equations here and from them this final differential equation, and then from it we can obtain the evolution of the input voltage and also the input current. We can see that the input voltage is going to follow an exponential evolution until the final value, which is the input voltage minus the voltage drop across the input resistance. And the input current is starting from a given initial value given by Vi over Ri, and then going exponentially until reaching the final value, which is equal to the average input current I prime. Regarding the AC components that we are going to have at the input, we can consider here the actual circuit in which we are considering now the current that is circulating here through the input of the actual SCC, like the total current including all the harmonics, not only the DC component but also the AC components of the current. So if we consider only the AC circuit, then the input voltage is going to be a short circuit. Here we are considering only the AC components of the current, then we have the input resistance and the equivalent capacitance. So we can analyze this circuit for each harmonic. And because usually the value of this impedance here of the input capacitance is going to be much lower than the value of the resistance Ri, then we can consider that the AC current that is going to circulate through the input is going to be almost zero, so that all the AC components are circulating through the input capacitor. Let's illustrate this with a simulation. Here we have again our inverter, and now we have placed here at the input series resistance of 0.2 ohms, 200 milliohms, and a parallel capacitor at the input of 1 millifarad. So let's run the simulation and see the waveforms. We can check, for example, the input voltage here, so we can see how it is increasing until reaching the final value, and we can also check the current circulating here at the input before the filter, RC filter, so we can also see how the currents start with a maximum value which is around 60 amperes and then reaching the final value in steady state. Now we can add another pane and check the current through the transistors, for example here transistor M1 and transistor M2. So now we see how the peak values here, the maximum value of the current, is much more limited than that without the filter. Here we can do a zoom and then see how the peak values are something like 78 amperes, which is a value that can be easily handled by this type of transistors. Remember that this is a transient period during the startup, so they are not going to handle this high current during a very long time. So when we reach the steady state operation, the currents are much lower, as we have seen before. Also note how the current through the resistance R2, the current here at the input, is free of high frequency harmonics because of the effect of the capacitor. So most of the harmonics are circulating through the capacitor at the input. Let's check here the current through this capacitor so we can see how the harmonics are circulating through capacitor C3. Of course, we are going to have some losses here due to the effect of this series resistance. Let's calculate the losses that we are going to have. For example, here we are going to add another pane and represent here the instantaneous power that we have in resistance R2. For this we can press the Alt key on the keyboard and then click, so we have here the instantaneous power. So we can see that the value that we are going to have in a steady state is something like 324 milliwatts, so this is not so high, and then we can keep a quite high efficiency in our converter. The other aspect that we are going to address in this video is the possibility of implementing bidirectional SCC converters. So we have seen in previous videos that switch capacitor converter can be bidirectional, but for this we need to implement bidirectional switches here for the 4 switches in our converters. So let's see how to do this, how to implement a bidirectional switch. Let's revisit first what is a bidirectional switch and what is not a bidirectional switch. Here we are showing an ideal bidirectional switch in which we can handle both current in both directions and also voltages in both directions. So the behavior on the IV plane will be like this. We can turn on and off the switch and we can handle both positive current when it is on and then also negative current when it is on. This is when we are applying a voltage VG, the control voltage equal to a positive voltage. And then when the switch is off, then we can also handle positive voltage and negative voltage. And this is when we are applying zero voltage to the control signal VG. We must take into account that a complete bidirectional switch is that one in which we can fully control the flow of the current in both directions, so we can turn on and turn off the switch at any moment. We can take as an example the conventional MOSFET in which we have the actual MOSFET in parallel with a diode. So we can see that the behavior will be like this. We have the actual MOSFET in which we can control the current through the channel by means of the VG signal, so we can activate and deactivate the conduction at any time. And then we have the diode in parallel, which is controlled directly by the voltage and the current themselves, and we have this characteristic as we know. So combining both together, we have this characteristic here in which we can see that this is not going to behave like ideal bidirectional switch, because in the first place, we don't have the possibility to interrupt at any moment the negative current that is circulating through the diode. And in the second place, we don't have the possibility to withstand negative voltage in this part of the characteristic, because the antiparallel diode will immediately start conducting. So we need to implement a real bidirectional switch. Here we can see a simple implementation of a bidirectional switch using two MOSFETs. So what we can do here is by applying a positive voltage, then both transistors, the channels of both transistors are going to conduct. So we have possibility of conducting current in this direction, and also the possibility of conducting current in the reverse direction. And then when we apply zero voltage here to the gates of the transistors, then the channels are going to be open, so it is not possible to conduct current because both diodes are in anti-series. Let's investigate this arrangement a little bit further. Here we can see the equivalent circuits at the on and off states. So when we are applying positive voltage to the gates, then both channels are going to conduct, so we have these equivalent resistances in parallel with the diodes. So it is possible to handle, as we have seen, current in this direction and also in the reverse direction. When the current enters here through T1, then of course the current is going through this series resistance RDS, and this diode cannot conduct the current. But in this other situation here, the current in principle can go through both the series resistance RDS and also through the diode. This diode in principle is not going to conduct as long as the voltage here across this series resistance is lower than the threshold voltage of the diode. And in principle, this is going to happen in most situations. The equivalent circuit is like this. I'm not going to enter into more detail because this has been explained previously in this other video, Power Electronics number 14. So if you want more information, please take a look at this video. And in the reverse situation, when the current goes like this, then it is a similar situation. In this case, the current can also be split into the RDS and the anti-parallel diode. But usually the current goes mainly through RDS because the voltage is not going to be so high. And then we have the other situation in which we are applying zero voltage to the gates, so both channels are open and it is possible for the structure to withstand voltage in both directions. For example, if we apply voltage here like this, then this diode here is going to be reversed biased, and this is going to be forward biased. So this is the diode, and this is the part of the structure that is going to handle the voltage. And in the other direction, if we apply voltage like this, then in this case, this is the diode that is going to be reversed biased. So the voltage is going to be withstand by this part of the structure, and this diode is forward biased, so we don't have a voltage drop here. So as we can see, we have a fully bidirectional switch here. It is very easy to implement because we only need one driving voltage here, VG. So now let's see a couple of simulations to check the behavior of this bidirectional switch in a switch capacitor converter. Here we can see the implementation in LTspice of the bidirectional switches. So we can do a simulation and see the output voltage, so we can see how we can get negative output voltage. And also let's check the bidirectional operation by taking the voltage to the output and then the load to the input, and then redo the connections, and then taking this one, I'm going to rotate it so it is going to be in the correct direction. So now we can run and see now the output voltage, of course, is minus 12 volts, and now the input voltage is getting now the positive voltage as expected. Let's now compare the operation of the bidirectional converter as shown here with the unidirectional converter implemented with 2 transistors and 2 diodes, and we're going to see how the bidirectional converter performs better than the unidirectional converters in terms of output voltage level and in terms of efficiency. Let's run this simulation. So we can see, for example, the output voltage here, and then go to this one and run also the simulation and see the output voltage. So we can see that here the output voltage, the average output voltage is around 10.3 volts, while here the average output voltage is around 10.9 volts. This is because here we are using the bidirectional switches, so we don't have voltage drop in the diodes as we have here in the unidirectional implementation. By using these diodes we have this voltage drop, so we have something like 0.4, 0.5 volts less at the output. And then in terms of efficiency, if we go to the bidirectional converter and press Ctrl L, we can see here the efficiency that is reaching 89.6%, which is quite good. If we go to this other implementation, the unidirectional implementation, and press Ctrl L, we can see that the efficiency is much lower, it's only 80.3%. This is because the diodes are having quite high losses and decreasing the efficiency of our converter. So in principle, the implementation with bidirectional switches is advantageous. We can get a better performance for our converter. And finally, we're going to do a last simulation trying to find the best operating frequency for our converter, for our bidirectional converter. So what we are going to do is to do several simulations to reach steady state at different operating frequencies. So starting from 100 kHz up to 1 MHz, and then we will represent the efficiency of our converter and see where the efficiency is maximum. As we have seen in previous videos, there are two opposite effects on the efficiency of this type of converters. If we increase the efficiency, the equivalent resistance of the switch capacitor converters is going to decrease, so the losses are going to decrease. But on the other hand, if we increase the frequency, the switching losses in the switches are going to increase. So there is an optimum frequency that we can select to maximize the efficiency. Let's see this in this simulation. This is going to take some time because we need to do a total of 11 simulations. We can take a look at the output voltage for each simulation. So now it's ready, so we can go to our log file by pressing Ctrl L. So we have here all the information that we have calculated. We have here the efficiency, but we can represent this by right clicking on the mouse and then selecting this option, and then add traces and select the efficiency, which is here. So we can see in green how the efficiency is increasing when we increase the operating frequency. The maximum value will be around here, so it can reach almost 96% at around a frequency around 500 kHz. So this will be the optimum operating frequency for our converter. If we increase the frequency beyond this value, then the efficiency is going to decrease because we are increasing the switching losses. Okay, this is all today. I hope this video is useful for you. Please let me know on the comment section if you have any question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.